In this first numerical example, we are going to continue with the first modeling example that we looked at earlier in this section. So we have here that basic, simple spring mass damper system. So we want to use its state space model and now numerically simulate the behavior of the system. And we're just going to kind of explore different parameters in this example. We don't have specific mass spring damping coefficients that we're going to be using, but seeing how changing them is going to affect its behavior. We're going to look at how changing the input into the system, what that U of t is, affects its behavior. And because we're in a state space model, we can have non-zero initial conditions that we can apply, so we can see how the initial conditions also affect the behavior of this system. So first thing is, we'll start with the state space model that we previously created. So let's just revisit what the state space model was in this system. So we have first our state equation, our x dot equals ax plus bu. We previously went through the steps. We found that A matrix and that B matrix, and we identified the state vector, the state variables were going to be the position and the velocity of the mass. So x1 was the position, x2 the velocity. And we have one input u1. And going through the steps, we got the A matrix, the B matrix. A was 2 by 2. We had two state variables, so therefore A is square. It's the number of state variables by the number of state variables. And B is the number of state variables by the number of inputs, 2 by 1. Then we have our observability equation, or our output equation, y equals cx plus du. We're told in this one the one degree of freedom that we're going to be tracking or sensing is the position, y, which has the state variable equivalent x1. So we found then the C matrix was 1, 0, and the D matrix was just 0. Again, the C matrix is going to be the number of rows equal to the number of observables or outputs, 1, and the number of columns equal to the number of state variables, 2. And the D matrix will be the number of observables, 1, by the number of inputs, 1. So D is actually just 0, scalar 0, but D will potentially also be a matrix. So what we're going to do is take this entire state space model and we'll bring it into MATLAB to solve our system of ordinary differential equations that the state space model created. In MATLAB, I am going to start by making an M file that is really the state equation. The job of this first M file, this function, is going to be to define my x dot terms. So here, it's a function file, so I have to name it as such. So I'm going to call this L09 for lecture 9, ODE1A, for example, 1A. And this is going to take inputs of t, time, and x. That is going to be my state. Now, we could have it take more inputs, and we'll see in later examples that we do that. We could have this take also as inputs the m, the b, and the k that we want to use. In this example, though, I'm just going to code those right into this function file and edit it as such. So let's see what this function file does. First, and this is kind of an optional step, or we could do this outside of the function, I'm defining the m, the b, and the k that I want to use. I'm right now just arbitrarily picking values so that we can explore this system. So we'll just start by making m2, k and b both 20 in the base units for this system, and I'll use SI units, so kilograms, newtons, and seconds, and meters for distance. Then I'm going to define my input into the system. Right now I've commented out the first one. We're going to start by having no external input, so the u is going to be 0. And notice the way I'm doing this is I'm going to always be defining u as an inline function or an anonymous function. So I'm going to make it a function of t in general. There's different ways you can define the function. I think this is fairly easy to do and to implement so that it's always going to be drawing the time properly from the model. Now here's what we do need definitely in this function. We need to have that A and that B as defined in the state equation. So A, I just transcribed directly from what we had previously. So it's the matrix 0, 1, negative k over m, negative b over m. And again, A is going to be 2 by 2. And then I define my B vector. This is going to be a column vector, 2 by 1. So it's 0. And again, the semicolon is going to denote that it is a line break, and then 1 over m. Let me run just this just so we can see the shape of everything. Okay, so if I print out A, yes, it's 2 by 2, and in this particular case, we get 0, 1, negative 10, negative 10. And B is indeed a column vector that matches what it should be for these particular parameters. And then finally, I need to define the output of this function. The output is x dot, I'm calling it xd here, which is going to also be a column vector 2 by 1. So because this is a linear system, I was able to put it into this matrix form. I can write it as ax, or a times x, plus b times u. And in this case, I have only one input, so I can directly just put u of t here. If I have a multi-input system, I would need a vector of u values that is my input vector. But here again, it is just a scalar. All right, so we define by this function the x dot term with inputs of t and x. And I'll talk about in a second, again, numerically, programmatically, what is this actually doing? All right, I'm going to put this function away for a moment and go to what I will call the driver file. The driver file is what is going to call the function we just made. So this is really the main thrust of what the driver is going to be doing. It's calling the ODE45 function in MATLAB. That is the function that solves ordinary differential equations, or at least it's one function that solves ordinary differential equations. So let's see how we use this and then see what it does. So let's start with the inputs. So first, in this first argument, or this first input here, I am going to tell ODE45 what is the name of the function that defines x dot. So what is the function that defines my state equation? That's the function that we just made. So I'm telling it here the name of the function we just made, the ODE45's L09 ODE1A, and I have to tell it also the inputs that it takes. I designed it to take only t and x as inputs. Now, also importantly here, I'm putting in front of that this at t comma x. What this function handle does is it tells ODE45 what are the names of the variables for time and the state in that order. So I'm saying that t is my time variable, x is my state variable, and notice that this t and x matches the t and x here. Now, in the way the function is defined, I don't have to put t first and then x. I do have to do that for the function handle, but here I could have defined it as x comma t. But I think it's easier to define it in this consistent order of t and then x, and then if we have other variables, like we'll see later, put those third, fourth, fifth, and whatever. But I like to do t first and then x. But again, this function handle will tell ODE45 time is called t and the state is called x. All right, so that is just what is the state equation to be using inside of ODE45. Then this next segment here, in the next comma, the next argument, this is where I tell it the time span to do my simulation, or in this case, I've defined it as the actual times to run the simulation. I'm saying start at time is 0, increment by steps of 0.01 seconds until 10 seconds has elapsed. And this is going to then give me values of my state variables at each of these time steps. We'll see what happens if I change that, what it does. And then third, I have to tell it the initial conditions. So what are the initial values of my state variables? In this example, I have those two state variables, x1, x2. So we're going to start by, in exploring this one, I'm going to set x1, the position initially to -1. So that is going to be -1 units above the equilibrium point, and then 0 for my velocity, or x2 value. So initially, we'll start it at 0. And then let's look at the outputs on the left-hand side. It's going to give me, or at least I'm using two outputs here. The first one is going to be the time stamps, I'll call it, of the times at which I have solved for my state variables. And then the second output I'm calling capital X here. Those are going to be the values of my state variables at each of those corresponding times. When we run this, we can see how it looks. But that X variable, as I'm calling it here, is going to have the number of columns equal to the number of state variables I have. So each column corresponds to one of my state variables. and it will have as many rows as I have timestamps. Again, here I'm specifying what times to use. I don't have to do that. I can just give it a start and a stop time and let ODE45 decide the best time steps to use in between. But we'll explore that in a moment. So essentially, this line 5 is going to solve my state equation numerically at the times I specify or in the time range I specify. So let's try running just 5 just to see what this looks like before we go further in what is happening. So I am going to clear everything out and run this. And it's run. If I look at my workspace, I now have a t, I have an x. So notice that t is 1001 by 1 values. Again, that's because I specified these timestamps here. If I print out the values of t, as expected, it stops at 10. If I scroll all the way up, it starts at 1. And it has these steps in between of 0.01 seconds. So it did exactly what I asked of it. So those are the timestamps at which I solved, and the x is 1001 by 2, so 1001 rows, each one corresponding to one of these times, and 2 columns, each corresponding to one of my state variables. So let's just print out x. So the first column, it's not very interesting at the end here, so maybe there's something better when I scroll up. Right, so the first column is my x1, which is position in this case. And the second column is x2, the velocity. So actually here, when we start, notice it starts at the initial condition. -1 for position, 0 for velocity, as it should. That's why I specified up here. Then the ODE, or the system of ODEs, takes over to solve for my x1s and x2 as time evolves forward. So how is it doing this? Well, this goes back to kind of the very basics of how the Runge-Kutta or the Euler method works. Now, ODE45 is doing more sophisticated things than the very basic premise, but the fundamentals of it are still going to apply. So what happens, we have our initial time 0, and we have our initial conditions. We have -1 for x1 and 0 for x2. So what we're going to do for that first time step, we want to know what happens for the second time step. So we have, let's say, time step 1. We want to know what happens at time step 2. So what ODE45 does is it's going to take our initial condition, or in this case, the state at time step 1, and it's going to put it into this model that we created. So it is feeding it our current value of x and our current time. So on the first step, our current time is 0. Our current state is the initial conditions, -1, 0 for this first example. It then calculates the A matrix and the B matrix, and then for this particular time step, calculates the x dot for this x and this t. Then what it does, like the previous purely numerical examples, we now know the derivative at this time. So we know x1 dot, we know x2 dot. So what we can do is we can take our current state x and add basically x dot times the time step. And that's going to give us the next state. That's going to give us our state at time equals 2, which is calculated at, for this one, we can go up here, our second state, which is 0.01 seconds later, is -0.9995 for x1, and x2 is 0.0951. So it's going to keep repeating this process. Now at state 2, it's going to call this function and now put in our new state. So x1 is -0.995, x2 is 0.0951. It's going to also put in the current time while we're at 0.01 seconds. It's going to make the A matrix, make the B matrix, and now it's going to compute a new x dot for this x, these states, and this time. So x dot potentially will be different. But now what we're going to compute is our state for the third time step. So we're going to take our current state of x, we're going to add to it x dot times our time step, and that will be now our third value of our state, as we see here. And this just keeps repeating until we have reached the desired end time. In this example right now, 10 seconds. So that's the very simple version of what ODE45 is doing. In the background, it is doing some more sophisticated error checking and error reduction in order to make the best estimate possible. That is definitely more involved than the very simple Euler step that we were looking at before, but that's the basic idea of what it's doing. It takes our current state, it calculates our derivative using our state equation, and then calculates our next state based on the current state, the derivative at our current state, and our time step. So we have our whole list of x's and t's. So that's just what line 5 does. It's doing the more or less Runge-Kutta Euler method in the background to get all of our states at all of our desired times. Now, we have basically our state variables x. What we can do now is, because we are really only observing x1 in this, I need to put in my C matrix and my D matrix. So those now can go in here for our observability or output equation. So we already found that C was 1, 0, D was 0, really scalar 0, and Y is going to be Cx plus Du. So notice here, just for simplicity, I did put the D because it was 0, but I'm not going to put the U in because for everything we look at in this class, the D is just going to be 0 or the 0 matrix. So actually, I really don't even need that there. But know that in general, there should be a D times U. It's just not going to affect anything we do in these examples. So it's really just the Cx. And do notice here, I have to transpose x because here x is coming out as 2 columns of values. And in order to properly use this, it really needs to be 2 rows of values. So I am doing C times x transpose. Then I'm taking that result and I'm going to transpose that. So let's just see what that looks like to get our y. So calculating y, I get the column. Really all it's doing in this one is picking out the first column of x because that is x1. But potentially if I have different C's going on, that might be the relative position of 2 masses, then the y can be more complicated than just being one of the columns of x. But we see y is 1000 by 1. That is the output that we were tracking, which was just the position of the mass. And finally, we can plot those results. I have my timestamps versus my observables, and let's just see what this looks like for this very first example. All right, so this is, again, I ran it for 10 seconds as specified, my displacement over time. Again, for this example, I am looking at, I have an initial condition, a non-zero initial condition, which we did not see before for transfer functions. But I'm starting at -1, which indeed I do in this example, start at -1. And what happens as time goes forward, my displacement is going to go up to and approach 0 as time goes forward. It's going to asymptotically approach 0. So this was a case with a non-zero initial condition, but no forcing acting on it. So we put our system above the equilibrium point, we let go, and it gradually reached its original equilibrium point at 0 given enough time. So by about, 6 seconds or so, it's very, very close to its equilibrium point after we let it go. Now let's change this up a little bit. Let's say we have a system that does start at 0, at equilibrium, like we've seen before for transfer functions, but now I'm going to change what my input is. Instead of 0, I'm going to give it a step input. I'll start at just t here. So the Heaviside function is just going to be 0 when the argument inside is negative, and it's 1 when the argument inside is positive. The Heaviside is basically the step function. So actually, let's just see what this looks like if I plot it, just so it makes a little bit of sense here. So t equals lin space. I'll start in negative time just so we can see what happens here. And let's plot t versus u of t. All right, so this is what it looks like. It's a little bit tough to see because the axes are so crammed together, but this is the value of u, so it's 0. You'll see when times are negative, and then it immediately jumps up to 1 when my times are positive. So this is our classic step function, and this is just a unit step function for this example. So at the moment, what have I changed from the previous run? I have a step input for u rather than nothing, and I will start at equilibrium at 0, 0. So let's run this. It looks, well, the picture kind of looks similar, but the values are different. Now I start at my equilibrium point at 0. I'm only looking at position here, so position 0. I immediately am applying this unit step function, and we see that the displacement is going to increase and gradually approach 0.05, asymptotically approach it from below 0.05. And given enough time, it's getting very, very close. It's showing 0.05 here, but it is getting infinitesimally closer to it as time goes forward. So we start at 0, and now we have a new static position because we keep applying this force as time goes forward, this constant 1 Newton or 1 unit force. Okay, so what happens if I change the parameters? Let me just kind of to foreshadow what we're going to be seeing as we get into Unit 2. Just out of interest, let's see what the eigenvalues are of the A matrix. We'll look at this in detail a little bit later, but let's just see what happens. Well, it's a 2 by 2 matrix. It's going to have 2 eigenvalues, and if we compute them for the problem that we just looked at, our eigenvalues are both real and both negative. So it doesn't really mean much to us now, but we can look at a pattern that's going to emerge. So both real and both negative. Let's play with the spring constant a little. Let me just increase it to 30. No real reason for that, but let's just see. Changing the parameters, that's the only thing I'll change. How does the response change? And we see here again we have this asymptotic approach. The new static value is different, but it's the same kind of general pattern that we're seeing. And let me go back into here and look at the eigenvalues of A. And they're both negative, and they're both real again for this different K and this, I guess that's all that changed was the K. So let me go back to that. All right, let me change a different parameter. Let's look at our damping coefficient. Instead of 20, let's lower that so that there's less damping. Let me lower it to 5. And let me, before I run it this time, let's see what the eigenvalues are of this A matrix when B changes. If we notice here, they are complex. They're complex conjugates of each other, and they are both in the left half plane. The real part of both of them is negative 1.25. So we have a complex conjugate pair in the left half plane when I lower B to 5. Let's see what happens when we simulate this with our solver. We see a definitely different behavior here. We start our equilibrium point at 0, 0, and we apply our step function immediately, and we have what we call an overshoot. We go above this eventual equilibrium position. We have an overshoot. We go down to an undershoot, and we bounce around near the new equilibrium point at 0.05. So we're bouncing around, we overshoot, we undershoot. Let's try a different B value, again, just to explore what's happening. Let's take a look at how that changes the A matrix and the eigenvalues of it. So when B is 8, again, we have complex conjugate pair of eigenvalues, both in the left half plane. And let's see what the behavior is going to look like. And again, we see for this these parameters, we again have this overshoot. We have a little bit less pronounced undershoot, and then we are approaching that steady state value of 0.05. So to kind of look forward in what we're going to see in analysis, when the A matrix had real left half plane eigenvalues, we did not see an overshoot or these oscillations in the system, but at least in these two examples, when we saw that we had eigenvalues that were complex conjugates and in the left half plane, we did have oscillations. And this is going to be true not just for these 4 examples we looked at, but really in all cases, the eigenvalues of A are going to tell us about the behavior of the system in general. And we'll see that as we go forward. All right, so we explored just kind of these having no input, having a simple step function input. And we saw what happens if we have initial conditions or don't have initial conditions. So last thing I'll do is let me just change this up. I can also just give it a range of values. So let's just say start at 0 and end at 8 and see what it does. So if I run that, look, it starts at 0, it ends at 8. Now I didn't in this one specify how many time steps to use in between 0 and 8. And if we look down here, it used 109. And they're not going to be evenly spaced in general. So let's just look at diff of t. This tells us the steps between each of them. So if we look, they're not constant. The time steps change in between neighboring points. If we don't specify the time steps to use, ODE45 will make a decision for us of how small of time steps to use. And it tries to do this in the fastest, most efficient way possible. So that's doing it in the least number of time steps, since that's what's going to slow down the use of ODE45. Now, for what we're doing, the time it takes to run this is not going to even be noticeable. So specifying all these extra time steps, not a big deal. But we can also let ODE45 make that choice for us if we just tell it when to start and when to stop. So again, going back to how it was before, I'm running it for 10 seconds and specifying all of the points to give me in the end.